Hello, in this video we're going to be using the general solution to natural and step responses to solve for this voltage across this capacitor over time. This is another example from the one previously. Just for a recap, that the general solution is this equation. It's the final variable plus the initial variable minus the final variable, e times e to the minus t over tau. Okay. Notice that in this equation we have an RC circuit. So in RC circuit, when we're looking for capacitors, we want to find the voltage across capacitors and currents through inductors. In this case, this is an RC circuit, so we want to find voltage across our capacitor. That would be our variable, our XF. So we want to have our final voltage plus our initial voltage minus our final voltage, e to the minus t over tau. So this would be voltage, right? Voltage. And for RC circuits, tau, their time constant, is RC. Simple as that. Okay. Now we have that the initial voltage in this capacitor is 2 volts. So this right here is 2 volts. We already found that. Now all we need to do is find the final voltage across this capacitor over time for t equals 0. See, okay. Let's use source transformation technique. Remember source transformation? We're taking Thevenin's equivalence and transforming it to Norton's equivalent and vice versa until we simplify this circuit. Okay. Let's start from the left side. We have this 24-volt voltage source in series with this 12-ohm resistor. Okay, let's do a source transformation. How do we do that? Using Ohm's law, remember V equals I R. We take the voltage. So we're going to transform this Thevenin's equivalent. I'm going to cut this part and take this and transform it into Norton's equivalent, where you have a current source. We'll have a current source and parallel with our resistor. Okay. We know that we reserve this resistor. This resistor will be the same, so it would be 12 ohms. But what is the current? Well, using Ohm's law, we take 24 volts, and we divide it by its resistance, 12, is equal to its current, which is 24 divided by 12 is 2. So we have 2 amps as the current. So that's equal to our current. So our current source, Norton's equivalent, would be a 2 amp current source in parallel with this 12 ohm resistor, and then we add back the rest of the circuit. Okay, so we have a 4 amp, and a 4 ohm resistor, and this capacitor. And then we have our 6 ohms and 36 volts. Okay, 6 ohms and 36 volts. Okay. Now, just a little trick for you guys to know that when you have currents or independent current sources in parallel, you can add them up. You can add these current sources up. If you have voltage sources, independent voltage sources in series, you can add them up. Okay, simply, see, we have this 2 amp current source going up this way, and we have this 4 amp current source going down. So if we add these two together, this is going in the opposite direction of this, we would have negative 2 amps, negative 2 amp current source going up with a 12 ohm resistor, and parallel with, what do we have, a 4 ohm resistor. 4 ohm resistor, and that would be in parallel with our capacitor, and 6 ohm resistor, and our voltage source. Okay, 36 volt source. Okay, now let's simplify these two resistors in parallel. And so this R equivalent would be, well, we have two resistors in parallel, we can just multiply their values and add the values and divided by the sum of the values. We get 24, excuse me, 12 times 4, 48, divided by 12 plus 4, 16. And we have 48 divided by 16, we have 3 ohms. Okay, so 3 ohms here. So let's redraw the circuit. Negative 2 amps, 3 ohms, and our capacitor, 6 ohm resistor, and 36 volt voltage source. Okay, 36 volt voltage source. Okay, and let's do source transformation on the right side now, on this side of the circuit. So we have 2 amps current source, and with this 3. Okay, so to do source transformation here, we use Ohm's law, V equals IR, simply. And this would be a Thevenin's equivalent. Now we have to transform it into a Norton's equivalent. So it'd be the resistor, 6 ohm resistor in parallel with a current source. What's the current source? Well, we have to divide 36 volts divided by its resistance, 6. 36 divided by 6 is 6, so we have 6 amps, right? Because your voltage divided by your resistance is your current. So 6 amps here, going up. And we can see that this current source is in parallel with this current source, and this resistor in parallel with this resistor. So we simplify these. So 6, since these are going in the same direction, we have 6 minus 2, which is 4 amp current source. And what do we have? What's the value for our resistor? Two resistors in parallel. 3 times 6 divided by 3 plus 6. And we have 3 times 6, 18 divided by 9. So we have 2 ohms. 2 ohms, right? 2 ohms. 2 ohm resistor. So 2 ohm resistor and our capacitor. What is our value of our capacitor? 10 millifarads. 10 millifarads. 10 millifarads. Okay. Now let's transform this left side back into its Thevenin's equivalence. Okay, so it'll be a voltage source in series with this 2 ohm resistor. And what's our voltage? So what's the value for our voltage source? Well, it's V equals IR. What's our current? 4 amps times our resistance is 8. So we have 8 volts. And our 10 millifarads capacitor. 10 millifarads capacitor. Okay? Okay, now that we simplified our circuit down to this simple circuit, we can find our, what we're finding? Our final voltage. Okay, final voltage across our capacitor. Well, if you remember that under steady state for a long time, for t greater than 0, so if this were to run for time to infinity, this capacitor would pop open. So essentially, what we have here is a 8 volt voltage source and 2 ohms, and since the capacitor pops open, this calls A and this calls B. Well, what's the voltage across A and B? It's simply 8 volts. So VC to infinity, as time goes on, we have 8 volts. Okay? And now that we have a final value for our voltage, we need to find tau. Tau is RC. Tau is RC. Actually our Thevenins times C. What's our Thevenins? Well, we just found here using source transformation, 2 ohms. So this will be that tau is equal to 2 ohms times 10 millifarads, or 10 times 10 to the third, we get 0.02. Okay? 0.02. 0.02 seconds, actually. Seconds. And now when we rewrite it into our general solution, remember, it's our final value, 8 plus our initial voltage, initial value was 2 volts. 2 volts. 2 minus our final value, which is 8 volts. So VC, the voltage across the capacitor over time, is final value plus times our plus 2 initial value minus the final value times E, and then minus T over tau, right? T over tau. T over tau. Okay. What's our tau? Well, we found tau is RC because it's an RC circuit. It's 0.02. So simplify this. Equal to 8 plus -6 e to the minus t over 0.02 volts for t greater than 0. There we go. That is our general solution for the voltage across this capacitor over time. Now, we could have found this R Thevenins for tau, R Thevenins, easily, because we have independent sources. Now, to do this is that we take all independent sources and we zero them out. We zero voltage sources by shorting, zero current sources by opening, and then we just find the equivalent resistance across A and B. Okay, don't forget to remove our load, zero out our sources, independent sources, and solve for our equivalent resistance. And this only works when you have only independent sources. If you have dependent sources, you cannot use this little trick. So to do this, okay, let's do this quickly. So we have remove our capacitor. So we have A and we have B, and what we have 4 ohm resistor, 4 ohms, and zero out this current source by opening it. So we'll have an open circuit at that point, and then a 12 ohm resistor, 12, and then we zero out this voltage source by shorting it, replacing it by a short wire. Okay, and then then we have this 6 ohm resistor and 36 volt voltage source. Zero out voltage source by shorting it. So we have 6 ohms. And simply we have this 12 ohm resistor in parallel with 4 ohm resistor in parallel with 6 ohm resistor. And when we get our equivalent resistance, so we have 12 in parallel with 4 in parallel with 6, our Thevenins simply 2 ohms, just like what we got here. Okay, and that's how you do it for this RC circuit. And thank you for watching.